whatever, I can't be happy, so I was like, should I? But, I think flexible one, either called Rochambeau, you can sell them through Shield, you can order them, or the ones that fit the glasses or sunglasses, you can order sunglasses in your prescription as well, and but they flex. I just have, my husband keeps bugging me. When I'm not. No problem with breaking with medical claims. Why I get, but. Yeah, you alone.
Welcome back, folks. Looks like we can get started. I hope you all had a restful Labor Day holiday and all that. Any questions at all to start us out? Okay, well, for the announcements, I don't have too much other than our first quiz is due tomorrow. It's this one right over here, and clicking it will reveal the PDF to work on it. And I should have the second quiz posted early morning tomorrow as well. So we'll be getting on a routine of weekly quizzes, not daily. And that's about how they'll go. They'll usually be posted on the very, very bottom. It'll involve material that is usually within this week. Well, any questions at all about the announcements so far? Okay, other thing I wanted to mention, let's get rid of this stuff. So we're getting closer to the first exam. This one is going to be on Monday, September 16th. And so that means this week is kind of special for me. It means when I get closer to about, well, we're just about there, right around Friday, I'm going to do the grade for all my classes and then switch gears for the rest of the weekend. Before here, you'll start seeing more information posted about exam one, the definite coverage, which sections. Then you'll start seeing material along the lines of review questions that you should take a look at for the exam. I'll probably give different options. So one version of a sample exam problems, then a second version. And all that stuff, again, should be posted over the weekend. So if you want to get started studying early, you'll have that opportunity. Any questions about that so far, folks? Okay, so that means let's take another look at the week. We don't have review days built into our schedule in the day-by-day syllabus, but I'm never opposed to an impromptu review day. In fact, we start every class with questions, and if we are on this day, a week away, then we're just right before exam one. If folks have a lot of questions relative to exam one on the 12th, then I'd say that's perfectly fine time to spend on the class meeting, so we can have an impromptu review day on that particular day. I'll mention that again, but it's just a reminder to keep in mind. Before the exam, if you come prepared with questions, then we'll be happy to address all of them, even if it ends up taking the entire class period. So that's how this course is going to be built up. Essentially, every week is a resource, and then as we get closer and closer to the exam due date, the information will propagate once again. I think I ran out of announcements, though. Any questions or comments so far, folks? Okay, well, where we left off on was, I believe, the second example in section 2.4. We're really nearly done with chapter 2. I decided to spend a little bit more time than what the day-by-day syllabus indicated, but I'm going through this book for the first time since 2019, so we'll make the adjustments that we need to make in the schedule. If we take extra time on a section, then I usually think that's always well worth it. So back to where we left off. We were using the calculator for the first time in a very big way, so we're getting back to that. And we calculate our very first set of summary statistics. If you didn't see how it was done, or if it got a little vague or foggy, don't worry, we'll be doing that a lot today as we go through the other problems like this one, as well as in the next section. So we'll have plenty to review on how all that goes. But I wanted to return to this problem just for a moment to give a feel for what did we calculate? Sometimes that's the biggest challenge in statistics, and we found a sample mean, 27.13. We were told above on the notes that that somehow measures the center. Then we also calculated the median. We said it's the 50th percentile, but that also measures the center, and now suddenly that becomes a little bit vague. If there's two ways to measure the center, which one did it the best? That depends on the actual shape of the data, how symmetric it is or how skewed it is, directs us on what statistic really represents the center. If we were to just point at the center visually, where would you say it should be? Would it be out here or somewhere out here? between 20 and 40, somewhere out here. Oh, I was supposed to draw on that. So visually, I think that's a good value since the area to the left of that is about half of the area to the right of that between 20 and 40. And in fact, that's what the median was trying to calculate. The median right at 21. So that's about, let's see, 30, pretty much right here. So this is the median at value 21. It produces a line that goes upwards like this. Yeah, imagine it's a perfectly vertical line. I'm going to do a redo on that. There we go. There's my perfectly vertical line. And now all the area to the left, so all that area is half of all this area that you see to the right, including that one outlier. So the median, this is equal to the 50th percentile. And now we're going back to this definition. What did we mean by the 50th percentile? We meant it's a number so that half of these values, let's see, this is not sorted, but half of these values should be below that number. On the histogram, it just means half of the area is to the left of that vertical line here, and half is to the right. So that's what the median found for us. That one location, let's actually leave the area shading there. Any questions about that so far, folks? Okay, so the median is either you split your data set in half and found a number where half is below or half is above, or on the histogram, it split the area of the rectangles in half. So that gives us another interesting comment to make now. What did the sample mean actually calculate? Well, notice it's pretty far to the right. Y bar would be, let's see, 27.35. Maybe not too far, but definitely moved to the right. Right there's about 30, so I'm going to just move that tick mark slightly to the left. So this is Y bar, the sample mean. Notice there is a little bit of a discrepancy between the two. Any volunteers for what could be the cause? Why would Y bar move to the right?
No, I don't know if the mean was the median.
It's exactly that, absolutely. This outlier, and in addition to that, these observations here cause all the data to be skewed to the right. Let's use this orange pen just to say we're adding extra notes. This isn't part of the questions we were answering, but our data is skewed to the right. And it's very curious that we also found that the median is less than the sample mean. In other words, Y bar is greater, and it happens to be only because of the skew in this problem. The worse the skew gets, the further Y bar just starts taking off and moving to the right. But we can still have the median represented well by the center in this kind of situation. So for these kinds of data, it looks like the median is actually doing a better job in spirit of measuring the center than the sample mean actually was. And again, it's all because of the skew. And this is what we were mentioning earlier. When your data becomes highly skewed, statistics gets harder, and this is part of the reason. The sample mean Y bar becomes less a great measure of the center, and you have to redo all of your formulas in a different way. But that was just a related comment after finishing off these notes, or this example one rather. Any questions, folks, about what's happening there with the graphics here? Okay, well, returning to those ideas, that's the purpose of this table here on example 2. This is one of those complete the following tables kind of problems, which means it probably won't make a good quiz, exam, or math stats lab problem either. What was that? My stats lab, I think is what it is. Forget what they call that thing. Let's refresh. Somewhere in there, we'll come back to that. But for this situation over here, this is more just for the sake of notes, just to fill out what's going to go on for related questions as they might come up. So we have 3 different situations. And again, this is the ideal case in the middle. Let's just put down a rough sketch. This is going to be roughly symmetric, it asks. Well, it says at least roughly symmetric, so we can make it pretty symmetric if we wanted to. I would consider that to be highly symmetric. Let's maybe even make it more symmetric with that value there. So if you have something that looks like this, at least roughly symmetric, There's three different options of what could happen. But in this case, we would have that the sample mean is approximately equal to the medium M. That means they're both doing a really great job. And so for this question here, what's the appropriate measure for the center? Most of the time, you would pick the sample mean Y bar. So here you could say Y bar is appropriate. But just a related concept, sometimes the median is still interesting in its own right, so the median could still be reported in this situation as well. They would be almost the same value, so if you reported one, you're giving information on the other. So more often than not, we would pick Y bar in this situation. But here's where it starts to go sideways. What about the skewed situations? Let's make something skew to the left. This one looks like it's violently left skewed. It's at a tremendous outlier just for good measure. If this is your graph, then something does happen between these two statistics. The sample mean is no longer approximately equal to the median. Which one would you say is the correct case? Which way does Y bar go? Exactly, it's going to move off to the left. It's going to be somewhere out here. So you'll have that the sample mean Y bar is less than the medium M. And just to convey that thought, let's say where the median M might be. Kind of hard to.
Is that always on left skew?
Yes, because the sample mean will always be less than the median.
Okay.
And I don't know if you can see it on your end, but my mouse seems to have frozen. Let's see what could fix that. Oh dear. Maybe it's this, the battery could be dying. I have another mouse up. Oh, so we have a bonus mouse, that's good. So back to this, I'm gonna have to put a new battery in this thing. I usually don't use this keyboard, it's a little awkward to get it up here, but we'll do the best we can. Sometimes you have to make adjustments on your best laid plans. I think that's pretty normal with all this technology we're using. So in this case, the sample mean Y bar will be strictly less than the median. And on the graph, if I had to pick where the median is, I'd probably say it's about somewhere around here. The sample mean, due to the huge amount of skew in this situation, it might be as far as somewhere right around here. We would need the numbers that go with this to really convey that. But that's what it would look like, much like with what we saw up here. We calculated the actual numbers, and with the right skew, we found, yeah, sure enough, the sample mean is greater than the median by a substantial amount, all because of the skew. Any questions so far, folks, with those two rows? I guess we haven't finished off this cell right here. So what about this situation? When the skew gets really, really bad, the best statistic people report, if they want to say, what is typical in this data? Where is everybody aggregating? They would more likely report the medium M in this kind of situation. Again, both statistics are interesting, but this one represents the center the best in this situation. Well, let's do one more, skew to the right. You can imagine for this one, let's give some context on this. Let's say this is income. And going this way, this is a histogram, so we'll call this frequency. I'll abbreviate it to FREQ for frequency. And let's say, well, I don't know what the scale is, but let's say maybe we have a first rectangle here to say most incomes are in some region, which is, I hope, above the poverty line or something along those lines. Then in a city like Idaho Falls, incomes start to drop off pretty rapidly, something like that. And now imagine someone like Bill Gates moves to town, maybe not quite that level of revenue, but they would have something over here. Suddenly one person with a huge net worth moving to Idaho Falls would make the income histogram of all Idaho Falls households or residents violently right skewed in this kind of way. In this case, what would you say is larger, Y bar or M? Absolutely, Y bar is the largest quantity this time. So I'll convey it this way, Y bar greater than M. If you're not a big fan of less than, greater than, that's never a big issue in this class. You could just simply write out Y bar is larger than M, and that'd be just fine with me as well. But for this particular graph, the median is probably maybe somewhere out here, roughly estimating. Y bar can move again pretty far out. This time, due to the extreme nature of the outlier, it probably moved to this distance away from the main grouping of data entirely. So you could have data that looks like this. The median is actually within your data. The sample mean could be an area where no data even exists, all due to an influential outlier like this one. Well, those are interesting things to mention, but the big takeaway with this graphic is if you have something that's at least roughly symmetric, so I'll highlight the whole thing, Y bar is a great measure of the center. But when things become skewed, whether they're substantially skewed or just skewed enough you never say roughly symmetric, you'd be using the median in both of those cases. So think sample mean for symmetric, at least roughly symmetric, median for clearly skewed data. Well, that's the purpose of example 2, just to fill out this. And there's plenty of questions you might see as just an additional part in the My Stats Lab homework, where they might ask you which statistic is better. And it's really going along these kind of ideas. Any questions at all, folks, with this example 2?
For the skewed ones, you said the means are usually used to measure the appropriate center.
It would be the median M for skewed, yeah. And you know what, now that you mention that, because we're just learning these ideas, it's probably good to add to the notes Y bar equals sample mean. I mean, this is the second page where we're really using these ideas. M equals the median. And it's always a good reminder when you think median that this is the 50th percentile. Other questions so far, folks, on example 2? Okay, well, let's put these ideas into work. For example 3, here's some pretty serious data. It's concerning when I read this kind of problem because I'm at an age where early onset dementia could be a reality. Your reality can change pretty quickly from one year to the next, who knows? And this says, to start out with the context, dementia is the loss of intellectual and social abilities severe enough to interfere with judgment, behavior, and daily functioning. So if you've had an elder in your family who's had dementia, you know exactly what they're talking about. If you don't, then that's a helpful definition. Alzheimer's disease is probably one of the more common ones, according to this, probably one of the more devastating ones is what I was going to say. And now it goes on in the article, living with early onset dementia. So that article right here, the authors Keaty explored experience and struggles of people diagnosed with dementia and their families. So that's really important data. And they tell us we have a simple random sample of 21 people. So they indicate a sample size, N is 21, with early onset dementia, and gave the following age at diagnosis in years. You know, this part right here is probably highlight worthy. It's the following data on age of diagnosis. Let's highlight that right there. So when you look at all these numbers, every one of these people were diagnosed with early onset dementia. Let me make sure that's how they said it. Yes, early onset of dementia. This person was diagnosed at age 60. That's pretty rough, really. But other people have a pretty terrible reality. You can be diagnosed with that at age 41. Could be Alzheimer's disease even as early as that age. So it's a pretty rough, serious data we're looking at. But keep in mind, when you look at any one of these numbers, that's what you're dealing with. The age at diagnosis for early onset of dementia. Well, here's all these data now presented as a histogram. It's hard to really process what this is saying. But in the histogram, we know that there's definite patterns going on here. For example, early onset of dementia seems to peak majorly between the ages of 55 and 60. And it looks like this is another slight peak here as well. I'd potentially be tempted to call it unimodal, but it's really debatable. This looks like it'd be enough for bimodal data. I would accept that as a correct answer as well, if we were describing the shape. But you know what, let's describe it anyways, even though it's not part of this question. What would you all say to this? Does it feel like unimodal or bimodal? Any volunteers to make the major assessment on that? Unimodal, I think that's a pretty good call. And it goes back to what we were saying in the prior notes. This becomes majorly bimodal the moment it just stands out more. If it looked like that, I would have called it bimodal for sure. But these data are borderline. I would accept multiple answers to borderline cases if it makes sense. Let's say this is unimodal. How about for shape? If it's unimodal, you're thinking of this as your main peak. Absolutely. Now it starts to reveal a left skew. And even though it's not necessary to say if you're mentioning shape, let's say that's what we're doing, just looking at the shape of this, it's still important for the sake of notes. I would say that there's no apparent outliers in these data. So let's say no outliers. To me, I would say it's not an outlier until this grouping right here moves, say, somewhere further away from the main group of data. So as it stands, it's definitely unusual, but I wouldn't consider an outlier for these data. Other questions so far? Okay, so now they're asking us which quantity is going to be larger, the median or the sample mean? Any volunteers for which is larger in this data set? I would agree with that. Because these data are left skewed, the sample mean is pulled to the left, whereas the median M is going to remain stable in its location. But you know, there's a lot of ways to answer this question. When it says briefly explain, you might have said Y bar because the data is skewed to the left. And that would qualify as a totally fine answer to that. Let's make that our official response. Oh, didn't mean to undo too much there. There we go. We'll say, well, which is larger? Well, that would be the median M. M, since Y bar is pulled to the left, due to left skew. That's one way to answer this question, but other people might have had a different view on this. We might have decided just calculate the sample mean, calculate the median, report them here, and that would have been a fine explanation as well. So unless the problem says specifically to explain it one way or the other, anything is on the table, anything you put down here that's correct would qualify as an answer. But the spirit of this problem was to look at it qualitatively, observe the left skew, and report a larger median M. Good news is we're going to verify that. We'll put this in the calculator and see if it's really true. But before we do that, before we see our statistics, it's good to know what are these statistics in relation to? What is the population and the sample once again? So let's try this out. Here's population, here's sample. I've noticed the way that a lot of times we address this question is we look to the sample. There's a random sample of size 21 people. And what about those people? Well, they all have age at diagnosis. So we might say for the sample, the 21 people in this study. But notice how very undescriptive that is. I'm just mentioning the sample size essentially when we say that, and the fact that they're people, not objects. But it's in population where we get to be a little bit more specific. Here, the sample came from the population. So if we describe this population well, we're also talking about the sample in a roundabout way. So here's the hard part, in my opinion. What would you say the actual population is for these data? I heard some good answers. Any others? Absolutely. Well, it's more about says here, the following data on age of diagnosis in years. So it looks like it's more about the actual person. But that's an important point to mention. They probably collected a lot of information, like how large is your family? Yeah,
So that's why. It's not just them. I don't know. But that is what it's at.
I see what you're saying. Yeah. So if you said the population is all people diagnosed with early onset of dementia, I would say that's the main thrust of it. But if you included and their families as well,
But they didn't do, the 21 people doesn't include and their families. That's just the 21 people diagnosed, so.
but yeah, the
But they would have had a
21.
lot more numbers than,
Sorry, say again, the with the numbers.
oh, I'm just saying that there would have been more people than 21 if they would have included their family members, I think.
Right, the family members would have had to
Right.
actually have the condition as well.
Yeah.
But the information about their family members was just a reminder that that's not all they collected. They probably collected a lot of information about their job, because that might tell them if they're exposed to certain chemicals, certain kinds of issues. They probably asked a lot of familial questions, because these kind of conditions, they're hereditary, they run in the family. You need to know a lot about what's going on with the family to get a better picture for every one of these 21 people. But yeah, if you just said here for population, all people, and I like how folks were saying diagnosed with early onset dementia, but I'd say that's a real thrust of what the population would be for this particular problem. I'd say the easiest thing to miss here, wouldn't take off a point necessarily in this problem, but it'd be a judgment call. But this word is actually pretty important where it was diagnosed. It means the population we're looking at is not perfectly targeted. There's a lot of people who will never get diagnosed with these conditions, and they go and live on their lives and just struggle immensely past these ages. So the population we're looking at is not all people with early onset of dementia. It's just the people who managed to get a diagnosis. Notice how unsatisfactory that is in a certain sense. There's limitations to science, which you can find out. And sometimes the population you have is not even the population you want. What they really wanted was everybody with early onset of diagnosis, but you would never really be able to measure that population. You have to diagnose these people to find them. It turns into a chicken and an egg problem. But nonetheless, we have some data. We can say something about this population. So we'll calculate the sample mean here just as an extra calculator problem. Also will help us verify if this was even a correct assessment at part A. But any other questions or additions with part B? Okay, well, let's practice this again. This is our second rodeo on importing data, crunching out statistics. First thing is turn on the calculator. Let me get rid of anything extraneous. And anyone recall what the very first button you have to click is? Absolutely, just hit the stat key. That gets you started. Immediately hit enter. I have some information in my calculator. You could just jam the delete key like we mentioned, but it's easier to go up arrow. L1 should be highlighted just like this. And avoid the delete button. You want to hit the clear button. Hit clear, and the next thing you'll notice is L1 equals blank. Just hit enter once you see your calculator is at that stage. Then it wipes it all out. And it's not the most important thing in the world, because you could just hit delete a bunch of times, but if you did a homework problem with 50 pieces of data and you brought that calculator to an exam setting, that's going to save you possibly 30 seconds right there. So it could make a big deal at the end of the day. Next thing you need to do is import the data. 21 observations, so let's go slow and get them all in. I'll try not to talk as I type them in, that might distract you. But again, this is sometimes the hardest part about doing homework in this class. If this was a quiz problem and your number was a little bit off, I would give full credit to that. If your number is majorly off, you could lose some points. But in my stats lab, the homework system, if I put in 60 wrong or just don't put enough digits, you could be off enough to miss the whole problem, which is frustrating. So take extra time right here, and it'll always make your work in web or my stats lab a little bit faster. So let me try to get these in. Okay, so here's where I do a slight check. I'm putting in my last number. If the sample size was 21, it should say L1 21. So the 21th observation, and then we should be all set. How are we doing on the calculator? Anyone need any additional time to put them in? Okay, looks like we're all set. And then how about another volunteer? What would you press very next to get this, to crank out data on that column? What's the next button to hit? Absolutely, just hit the stat key again. Now what we're doing is calculating something. So you need to hit the right arrow until the calc menu right here is toggled. It should just be highlighted like that. Yep, absolutely. Well, we're on option one. We just need option one to get all of our outputs. So on this screen, you're essentially just hitting enter a whole bunch of times. It should say L1 here. If this is empty, you can bring it back. So here I took away the L1. The way you bring it back is, let's see. There it is, L1. But I can't just hit 1. That's not going to work. The thing to notice about my calculator is L1 is in blue. Your color might be different depending on which model you have. But if the L1 is in blue, you have to hit the second key. Then come down here, press the number 1. It'll bring L1 back. So if anything weird like that happens, it's always fixable. Next, frequency list should be blank. And right where it says calculate, you just hit enter again. So this is what your calculator should look like. Depending on your model and how updated your model is, it should look like this. Anyone have a slightly different screen by chance on their calculator? Okay. Well, let's hit enter. This is what comes out. And it says it wants Y bar. That's a bit of confusion on these calculators. Let's do a screenshot just to clarify. Some books use X bar, and the author or the people who engineered this calculator were a fan of that book. Other books use Y bar for their sample mean. The country's divided on which is the best. So you just have to be able to adjust whenever different things come up. It's the bar that's important. So this problem, if I can get down here, there we go. Just for the sake of the notes, let's put down here. This is Y bar. So we pretty much have it. The sample mean Y bar is 52 point, and I'm not sure if I gave advice on rounding on these notes. I didn't say anything about rounding. So if this was a quiz problem or an exam problem, I'd say use your best judgment. For these data, I'd be willing to round to the nearest tenth of a year. That gives pretty good information. If you rounded to the nearest year and I didn't say anything about rounding, I'd still accept that for full credit at 53 years. But this is 52.5 years. And so that's the sample mean of these data. Well, we did it, folks. That's the end of calculating the center. Any questions at all so far? Okay. Well, let's also say, what did we really just do in a certain sense? When we mention the population right here, there's something also associated with the population. There's something that goes like this. This is the Greek letter mu, spelled this way in our letters. And if you're a person of science, you might notice that it looks like a micrometer or something like that. That's a common unit. But in statistics, the Greek letter mu refers to the population. Mu is going to be equal to the mean age at diagnosis for all, let's go back here, all of what? People with early onset dementia. I'm going to skip diagnosis since we only already said it once. So I'll say for all people with early onset dementia. Now, this quantity is almost impossible to calculate. Not because we don't know what the population is, we know what it is, But you would have to get every single person, say in the state of Idaho or in the United States. If this is an international population we're thinking about, now the problem is tremendously out of scope. Contact every single person with this condition and ask them their age at diagnosis. A study like that might just be too expensive to actually carry out. So they dealt with a sample of just 21 people. Calculated a sample mean of 52.5 years. And the reason you'd want to do that is now you can say mu. This is the average for the entire population, the population mean. It would be approximately equal to 52.5 years. And that's a pretty impressive statement. We know something about the population just by dealing with the sample. If the 21 people in the sample represented the population very well, then we have great confidence in this estimate. But there's still one thing that's majorly missing. This is why our statistics class is 3 credits, why we have to go a lot more beyond here. The trouble with this estimate is this estimate is useless. That's really sad to say, until we describe the error in making that estimate. We need to say how accurate is that estimate in the first place, and there's nothing we've done all class that's going to help us do that. Until we have a way to say what is the reliability of that estimate, until that can come into play, this estimate really doesn't help us a lot at all. That's kind of unfortunate. One thing you might have noticed in the news is that sometimes they don't report the mean, sometimes it's a proportion or a percentage. Think elections and things like that. Some people might say that whoever is 9 points ahead of the other candidate, and that's within margin of error. When they say margin of error, that's what they're trying to describe. How reliable is that estimate in the very first place? So that's what we're trying to get into with statistics. And the only way to complete this picture is it's not about just the center, it's about how spread out the data is as well. We need to measure how the data varies from one individual to the next. If we can do that, we can now attack this problem right here. But for the moment, this is the main takeaway. We're just getting used to reporting the statistics. Well, any questions at all, folks, on those computations? Okay, so this is the direction all this is kind of going in. And the reminder is, that's pretty much what we were discussing right here on these notes. Here, we were dealing with categorical data. P hat was just the proportion of people in favor, that's one category. Not in favor is the other category. And that's something you can calculate, and it would estimate a population percentage or proportion. But once again, until we describe the reliability in that estimate, it's still useless to us. That's really kind of tragic. But no worries, we'll spend about, week 3, so we've got 13 more weeks to show how this estimate really comes into play, how we're going to make that work. Well, let's move next to section 2.5, the last one of chapter 2. I took a lot more time in chapter 2 than I anticipated, but I think it's well worth it, because these are things that are going to come back all the time in the class. Population sample, the statistic here, and the quantity mu that we described. But let's go off next to variability. So section 2.4 was about the center. Section 2.5 is about the spread of the data. Let me first fix my windows here. This got revised in a really big way, since my old notes had X's here instead of Y's, and I did get the Y bars incorrectly, so at least that. My other revisions were, these were X's minus X bars. I had to change all of these to Y's. So if you printed these notes out early, the revision isn't major, it's just getting notation in line with our actual textbook we're all reading. So there's a lot being said here. Just like when we looked at the other notes, 2.4, there's multiple ways to measure how spread out the data is, the variability. One way to do it is this way. Through the range, we could just report the difference between the maximum value and the minimum value. That's one single number, and it's kind of a weird way to report the range. Sometimes people want the minimum and the maximum. But for reporting it as a statistic for how spread out data is, we just give one number, minimum minus the maximum. Tells us how spread out our data is. Well, this is here mainly because it's in the homework problems. It's not the major thing we're going to be looking at, but occasionally we might calculate the range of the data. Another one is going to be this, the sample variance. The sample variance comes in with the symbol S squared. And notice what it does. Y1, that's just your first piece of data. So for example, this would be Y1. That's your second piece of data, so that's Y2 and so on. But for every piece of data you have, we go and take the sample mean Y bar and subtract it from the data. In other words, Y bar is the center, and we want to know how far away is every piece of data from the center. We square that. The reason we have to square it is the numerator here would actually turn out to be a 0 without the power of 2, and that doesn't help us at all with measuring how spread out things are. So we square the differences from the observations and their centers, add them all up, and divide by n minus 1. In symbols, it looks more like that. The summation of every piece of data y subtracted from its sample mean and squared, then we divide by n minus 1. You might feel kind of weird about that because we've just looked at different sets of formulas where we divide by n. So this is kind of vague all of a sudden. Why n minus 1? There are a lot of reasons for that. But one reason is you could actually calculate s squared by deleting one piece of data. If I delete one piece of data, we could solve for it and actually still calculate s squared. We say that there is n minus 1 degrees of freedom in this data. But that's all really pretty vague kind of stuff. If you're extra curious about that, I would recommend taking a look at that video right there. It's purely an optional video, but it does a really great job with graphics and explanations of why in statistics we're dividing by n minus 1. It's a really technical kind of question. My explanation is the fast way to think about it, but there's more to say. But that's our second formula we have so far. Notice if you're using this formula, you also have y bar in the picture. So that means s squared and y bar are paired. So that's kind of interesting in a way. And let me put my bracket in the right correct spot. So here's my second measure. Here's measure number 2. And I have one thing missing in the notes. I kind of amazed I left it out. Anyone happen to know, just by exposure to statistics in your education, the thing that I missed right under? Well, there's another statistics that measures spread. The sample variance does a good job, but it has a defect. If your unit is in inches, because of that power 2 right there, your spread is in inches squared. That seems kind of strange. You have a unit in inches, but you're describing how things are spread out in squared inches. There's a correction to that, and it's called S. It's equal to the sample standard deviation, and it's defined in this way. S equals the square root of s squared. So whatever this number comes out as, if you square root it, you take the unit and you bring it back to the unit of the original data. So for example, if the original data was inches, this would be spread in inches as well. Makes interpretations just much more reasonable and easy to think about. And that's the statistic I missed down here in the notes. We'll just inject it. So like we mentioned before, s squared, let's say here, s squared, s, either one you might be using. We'll use s more often than not, but the standard deviation s is defined in the variance, so that's why we have both formulas. Those are paired now. Finally, we get down to the last one, something called the interquartile range. We'll abbreviate that one as IQR. And the interquartile range and M are paired. So imagine you have data that's highly skewed. We would probably report the center of that data using the medium M. And if we're using the medium M, we're not using the sample mean. It no longer represents the center well, so it will no longer represent the spread well either. It's just as damaged by skewed data. Instead, if our data is skewed, this represents the center well, M, the median, and it's paired with the interquartile range as well. So Q1 is the 25th percentile. Quartile 3 is the 75th percentile, and M is the 50th percentile. This all feels kind of weird and arbitrary, but for reasons of this is how they described statistics hundreds of years ago, M is not called quartile 2, even though it functions as quartile 2. We say quartile 1, then the median, and then we jump to quartile 3. Kind of weird. If you called M quartile 2, I think most people would know exactly what you're talking about, though. So there's 3 measures of how spread out the data are. In this problem, it's going to be much like the last section. We'll crank out data. We'll do one by hand, just to show how the formulas actually work, and then describe when to use what, and finalize with another example. So these notes are very similar to the last section, but now we're dealing with 2 statistics as well. We're dealing with spread and center all at the same time. Any questions at all, folks, about the formulas before we jump into a problem? It is quite a lot, yeah. The good news is we'll spend some time with it on these notes. And once we're in the prior chapters, the major things we'll be using is the standard deviation sample mean to describe center when we have nice enough data. But we're also going to be using these statistics here to come up with a rule of thumb for an outlier. It's going to be called the 1.5 IQR rule of thumb. That's in chapter 4, and the good news is we review this material again in chapter 4 to see how it goes all over again. But let's give this a try then. Example 1 says, biologists studying the healing of skin wounds measured the rate at which new cells closed a razor cut made in the skin of an anesthetized nude. So that said a lot in one sentence. So imagine how much data we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 18 nudes. Someone, a biologist, maybe a veterinarian, gave them a gas or an injection to anesthetize them so they'll feel no pain. Then another person grabbed probably an X-Acto knife, measured a cut and made an incision on every single one of those nudes. Then they measured the healing of skin wounds. They measured the rate at which the new cells closed. They measured how fast did they heal. So what it says here, here's the sort of data measured in micrometers per hour. That's what this is all mentioning. So for example, this newt has some kind of amazing healing factor. It healed at the rate of 40 micrometers per hour. I don't know how fast that is relative to humans healing a skin wound. Something with this newt was special. It healed at a much slower rate. Well, another thing to mention as well is watch out for this symbol. That is a unit. And then it gets conflated later on, as you just saw in the last section notes. Mu alone is what we'll call a parameter. It describes a population, whereas up here, just a unit. It's 1 times 10 to the power of -6, very small measurement. Well, that's the story of the data. They provide us a histogram of these data. What would you call these? Is this unimodal or bimodal in this situation? I would agree with that. And I think this one, in my opinion, would not be borderline. I think we would need to say bimodal for these in order to get full credit. We have a major peak here, major peak here. So it's bimodal data. And as far as the symmetry goes, I would say we have a touch of skew to the left. Would folks agree with that assessment? In that case, that part is a bit borderline. If you said roughly symmetric, it fits with these data, but I think I'd be more tempted to say slight skew to the left. No apparent outliers. I'll leave that off this time just to convey that's okay if you left that off, if they're asking about the shape. And now let's go to calculate each one of these statistics. Like before, that first step is turn on the calculator. In this menu, you could just hit the stat key and go right back where you need to be. Hit enter. Then just save a little bit of time, up arrow and the clear button. Enter again, and we've got all the data wiped out. And this does take some practice. We'll go carefully at first when we're learning this kind of stuff. But once we feel like we've got it down pat, like around midterms, we might do it a little bit faster so we're not just bored to tears every single time. But for the folks who need extra time to see how this goes, we'll take that extra time. I'll go row-wise. 11, 12. Oh, I shouldn't talk out loud. That could throw you off. I know that'd throw me off. Give folks a few more moments to get it in. Okay, well, if we have all the data in, you should see something like this, L119, if this is highlighted here, just to signify you're about to put in the 19th piece of data. So we're done. We only had 18 pieces. Hit stat button, right arrow, and then you're pretty much just jamming the enter key until your statistics show up. So enter through the list, enter to calculate it, and this is the result I got. This is a good time to just see how we did. Are folks getting about 25.6 repeating? Awesome, that says we're on the right track. So let's get these values in. And this example one is pretty in line with the first homework question in this particular section. They ask a lot of random statistics out of nowhere, so I did the relevant thing as well on this one. So calculate the mean. It's referring to this 25 point, it says 1 decimal place. So this would be at 25.7. Next, it wants the median. Anyone recall how we get the median to come out from the calculator? Sorry, say again?
Pull down.
Absolutely. So hit the down arrow key. And here we are. Notice Q1, Q3 came up. It's referring to quartile 1, the 20th percentile, quartile 3, the 75th percentile. But we wanted median, the median, and that one was
26.5.
awesome. So we got 26.5 here.
Round up the top, but we round up 7.
Well, if we're rounding to the, let's see, 1 decimal place, you would think over here as having a decimal place of zeros, really. So this one would stay stable. On this one, it's at 26.5. So down here, 26.5. When I'm doing something else with my color coding, so I'm going to put this back to black. 25.7. So this is the mean. We don't have to actually throw on a symbol. And sometimes our problems request it, but in this problem, it just wants the value. But you know what? It's not a bad idea to get in that habit, because when the formulas involve these quantities, it's good to just report what that symbol is for the related quantity. Also, it's good to check for consistency. We said skew to the left. That means this should be pulled to the left. It should be less than the median. And yeah, that looks about right. Not too far off, and that's why we said slight skew. If we said majorly skewed, we should expect these to be majorly different. So we've got two statistics down. Next, we need standard deviation. Here's where it gets a little bit foggy. In this list of numbers, what would you all say the standard deviation ought to be? Good call on that one. It's, as you said, this right here. Notice there is a sigma x right here. What is all the hell about? Let's take a screenshot and describe this a little bit better. But just to finish off the problem, let's put down here the standard deviation, S, equals this quantity, Sx, and it rounds to 8.3. I think we have a little bit more to say on that, so let me try to get a screenshot going. We'll just jam it right here. So here we have y bar in that location, summation x. This is if you had not divided by the number of observations, 18, you would have got that value. It's that value squared. If you squared all your observations, you squared 14, 18, and so on, add them up, you would get that quantity. But we really don't have anything to do with either of those two. We want to go down to this one. This is S. And just for the sake of notes, S is the sample. Standard, I'll often abbreviate as STD, deviation to DEV, just because those are really long words. That'll help with note taking. So what's the sigma? That's another one that's pretty interesting on here. Now let's put down this, just to tie the both together. Mu is the mean of, what's that F there, the population. Sigma, just another Greek word, is the standard deviation of the population. You'll always notice that when it comes to sigma x, the values are a little bit off. So what's happening with the sigma x value is, what the calculator did is it did not divide by n-1, it divided by n. If it did that, it's assuming that this is the entire population, but that's not the case. This is just a sample. So the sigma x here is kind of a curious thing to have inside your calculator, but keep in mind, it's because there is a difference in calculating the standard deviation for the entire population versus doing it with the sample. It should involve n-1, which means we always pick this quantity. Just circle it just for emphasis. So that's what's happening in the calculator. Well, next thing we want to calculate is range. Well, what's range? Let's write this out just for the sake of the notes. Good call, absolutely. We take max minus min. Now, this is not a hard one to do in the calculator or by hand, right? The maximum is 40, the minimum is 11 because the data is sorted. But the data is unsorted, you might miss something. I know I could miss a number. So here's another way to do it. Back in the calculator, just scroll all the way down to the bottom and it reveals your max and min once and for all. So it's going to be 40 minus 11. So this will give us a value of 29. So 29 is the range of the data. That just means from here to here has width 29. It does measure how spread out the data is, but not in a great way because it's not saying where the data clumps in here or here. This is taken into account when the data is clumping in certain regions. The standard deviation is 8.3. Well, any questions, folks, with calculating those statistics on example 1? Okay. Well, one thing that's kind of hard about these kinds of problems is we said the range measures how spread out the data is. And sure, the more this quantity moves to the right, the more spread out it becomes, the larger the range is. But what about S? S is the sample standard deviation, and it's not really telling us how it signifies how spread out the data is. But one thing it would tell us is the more spread out it becomes, the larger the number is, the less spread out, the smaller it becomes. And if this value is ever a 0, that can happen, but what it would mean is all observations are the same. So if we got a standard deviation of 0, that means this data set should have went 11, 11, 11, 18 times. No variation whatsoever, no spread in the data. So that's something you would almost never see with real data. If you did, well, it'd be really interesting how you got that data. Why is everything measured exactly the same amount? Never really happens in the real world. In the real world, there is always variation. We have a class of about 24 people, and I expect everybody is different in major ways. Variation, whether it's people, numbers, is just something we expect. So your standard deviation is always positive, but still, that number doesn't do a great job of saying how spread out the data is based on the number. So here's one thing you can say, just to get started on that question. If the data is at least roughly symmetric, sorry, say again? Oh, I missed you. I'm gonna have to come back to this. This was just an extra comment.
Oh,
But I'm gonna have to come back to that one. Thanks for mentioning it. Totally forgot it was there. Starting to get a little busy with the notes and everything we're putting down as screenshots. So here, if the data is at least roughly symmetric, then approximately 68% of observations are between y bar minus the standard deviation and y bar plus the standard deviation. So we go to the center, y bar, move a distance of 1 standard deviation to the left, that's the minus s, move a distance of 1 standard deviation to the right, that's the plus s, about 70%, 68% is what this is quoted as, of all your observations should lie within that particular range. So that's what the standard deviation is trying to do. We'll expand on this rule a whole bunch more, but I felt like just giving another number 8.3 doesn't do a lot unless you know what that number is saying. So coming back here, there's the sample mean, 25.7. It's about there. Let me go to second quit and go back to the calculator. Let's take 26.5, subtract the standard deviation, minus 8.3. We're at a lower end of 18.2. So about here, let's do the related thing and just add 8.3. By the way, this is a really fast trick in your calculator. Hit your up arrow, enter, move left and put plus, and this just, it's more about accuracy than speed. If I have to type these in a bunch of times, I'm probably going to make a mistake. But if you copy paste in that way, it just streamlines things and makes you more accurate. And it's faster as a bonus. So I'll mention that trick a lot as we use the calculator more and more. Here's the upper end at 35. So from here to here, we shade in those regions. This should be about 68% of all observations. So in the histogram, about 68% of the area. Would you agree that looks like 68% of area shaded? Roughly, it's not perfect. It did have skew. This was asking for roughly symmetric. So the more the skew, the worse off this is. But pictorially, that's what the standard deviation is trying to say in terms of the spread in your data. Well, I highlighted this in yellow since I forgot to answer part E. Thanks for mentioning that again. First, any questions, folks, with what we've calculated so far?
the actual SVP is budgeted. interquartile range, we would just write in between 18.2 and 34.8.
Oh, sorry, that was just for the standard deviation, those numbers there. So for the interquartile range, you have to go back into the calculator and get some new numbers. We need the first quartile and the third quartile to get that range. Any questions before we give that a try next? Okay, so for S, this is how it's conveyed over here. Let's do it all over again. Notice my stuff's gone, but you could just go back to stat, calculate, just make the calculator recalculate everything. Seems kind of cruel in a way, but it's quick at it. And here's the numbers back. We need to be on the last page. So I'll scroll all the way down to the bottom. And to do this computation, I'd probably start by going like this. IQR equals, this is one where we're using formulas a little bit more. So it's a good one to start writing down the formula. It's quartile 3 minus quartile 1. And if you got those backwards, it's okay. There's a fix to that. The interquartile range is always positive. It can never be a negative number. So if you got negative, just switch the order of the quartiles and you're in good shape. Where do we get the quartiles? Back up here in the calculator, we're just taking 22. Oh, hang on, I made a mistake. 33, the upper quartile, thank you, minus the lower one, Q1, which is 22. So we get a value of 11 altogether on this one. Any questions, folks, on that value so far? So just like it's challenging to describe the standard deviation, how it's mentioning spread, it can be challenging as well for the interquartile range. Oh, we have a chat first. Corey says, can you help me name after class to fix it? Yeah, I could give you a try, absolutely. So just stick around in Zoom and I'll be very happy to help. So last thing to lead with is, what is this number describing? We put just 2 more points on the graph. 33 is about here. I'll put it a little bit lower so it doesn't get too busy. 22 is over here. We have a range that goes from here to here. And this is the central 50% of observations. So the interquartile range tells you how long is the distance from here to here when you're capturing not the middle half, the central 50% of all observations lie between these two numbers. And this just tells us how long that range actually is. Well, any questions, folks, with all those statistics so far? Okay, it's quite a lot in this first example. We're comparing this mean, the median, standard deviation, and interquartile range. So in the next problems, we're going to start specializing after a by-handed question. I would say this is definitely a good stopping point for us today. Any last questions or comments at the moment? Okay, when we come back next class, we'll be finishing off these notes, then moving over into chapter 3. And hey, Courtney, you said that there's something weird in your calculator. Was it, say, on this page right here, where there's the data import stage?
Yeah, my columns where it says L1, it's blank and it just says name equals.
Gotcha. So the fix on that one is, first let me kind of do the same. You've got something that looks like this, right?
Yeah.
Okay, so the fix on this one is, go back to this screen by hitting the stat key.
Okay.
Then what you want to do is just hit option 5 and press enter a bunch of times. Set up editor, then hit enter on this screen, and something happens. It doesn't tell you what, but if you see this screen pop up, it should fix everything.
So
Are
then
you
just
able to see that screen?
Yeah, well, I pushed enter a lot of times, so it says set up editor done like 20 times. So
Yeah,
I just pushed stat afterward.
yeah. Then back to the edit, and you should see everything just came right back.
Okay, because on one of the examples, I somehow ended up in L3. So I just messed that up, I guess.
Gotcha. If that ever happens, you can go back over here to calculate. If you put it back to L1, then hit the second key in blue, the number 1, and it'll bring L1 back right here as well.
Okay, I tried. Yeah, okay. I couldn't figure out how to get it to do that.
Gotcha.
And then, well, I guess I can watch the recording. I was just trying to add the input, and so I wasn't quite sure after you hit put in all the information like in the L1. And then you said you go, well, maybe I'll watch the video, and then if I have questions, I'll email you.
Gotcha. With the last step, you'd want to go right here where it says calculate.
Okay, so then I just need to go, okay. And then just push enter.
Yeah, if your screen looks like this, you just hit enter a bunch of times again,
Okay.
and you should
Okay,
get this.
yeah, that's where I was like, I don't know how I'm not getting to that point. So, okay. I will do that. Okay.
Awesome. You know,
Thank you so much.
you betcha. Absolutely. Question over here?
Yeah. Kind of. Okay, so it's just a question for that first. I don't know how to get back into it. Maybe. There we go. Okay, assignments. Okay, so the first question on that one that I'm struggling with.
Oh, gotcha. Yeah.
Yeah, because it told me, I wanted to know how or why I did it wrong. Because I added all these up, I got all these numbers. And it told me that I needed to, I don't know if I did the wrong decimal points, like
They're
I
happy with
did,
the subcompact and mini.
yeah,
Interesting.
so I don't know.
And it said round to 2 decimal places. So let me give it a try along with you.
Yeah, because I
Let's
tried
check
it on
out
my
that
calculator.
second one.
Yeah.
So first thing I do is go 10, 19 plus 4633.
Plus 4579. Plus 2218. Plus 139.
Okay, so we've got our total number of cases, 12,588. So for the compact, I would go 4633.
125.
Exactly.
And then multiply that answer by 100.
So we've got
36.
36.80.
See, that's where I was confused because
Huh.
I thought I did it right, but
It looks right. At least on my end.
yeah.
So compact.
Because
measure-
I know they're a lot more like particular about the answers than you are,
Yeah.
so that's why I was like, what am I doing wrong?
Gives the number of passengers or car occupants killed in accidents in a certain year, convert the table to relative frequency, and they're happy with the first one. Let me try the first one.
Yeah, that's where I was confused.
The first one was
One divided by,
and we got 8.1 after rounding
yeah.
to 2 decimal places. Yeah, that would have rounded to 8.1. And this one to 2 decimal places should have
Which is
been,
0, so it's still 36.8.
yeah, weird. Just out of
Maybe it was
curiosity.
36.8 and not
Yeah, I was
80.
gonna ask you, do you think that could have been it? Want to give that a try, just in case?
Yeah, because that's what I was thinking.
Let me look at the third category as well,
Sure.
4579. And this one to 2 decimal places would be 36.38, which is exactly what you have. Geez. I'm gonna have to take a look at that problem in more detail. Sorry about the
Yeah,
trouble
well,
with that one.
I was talking to Tiffany. She
Looks
said-
like you're doing it right,
Yeah,
absolutely.
she sits next to me and we obviously all get different questions for the
Mhm.
homework questions.
But probably the same
But
issues though, right?
we did the same like type of problem and she even put my questions in her calculator, got the same thing. She goes, that should be right.
Yeah,
So-
I agree with her as
So
well.
that's why I wanted to ask, but
Yeah, it looks like this problem might just be actually bugged in this actual
yeah,
system.
cause I was like, cause it says round to 2 decimal places as needed. But then I kept getting it wrong and I was like, I don't get it.
Yeah, we'll take a look at this
Okay.
one at the start of class,
Okay.
but probably what I'll have to do is just give everyone credit on that problem. Looks
Okay.
like that one might be messed
Yeah,
up.
cause I mean, she got all the questions right, 1 through 5,
Mhm.
on that specific
It's
question.
just some people are getting it.
She got it right, and then
Yeah.
I was doing mine and I got it wrong, so I was like,
Well, I feel
What did I
you're
do?
actually doing them right. I couldn't
So-
find it what it would have been.
I appreciate it. Thank
I'll
you.
take a look into that and let you know.
I'll show you the quiz tonight, is that okay?
Yeah, that'd be perfectly fine. You bet. Have a good one.
You too.
Hello, folks. Not too bad. How are y'all doing?